All right. So we've got up here our theorem on conjugate pairs of zeros, and we've talked about this because this has to do with the i's in our roots when we have a factor that has an imaginary root that they always come in pairs. This is just the wordy definition for that. And the instructions of it feel weird, and this is essentially the way the book words the don't keep i's in your polynomial bit. So that's what the express f of x as a product of linear and quadratic polynomials with real coefficients irreducible over r. What this means is no i's but factor form. So as small of factors as you can have with no i's. So we're not going to be fully multiplying out on ones that have this instruction on there. But there's a section in the homework that says that. Express it as a product of linear and quadratic polynomials with real coefficients irreducible over r. So it's very similar to what we were doing last week, where we're going to take our zeros. So this first one we have is going to have 2, minus 1, and 3i as factors. So when we start writing this in our factored form, how are we going to start? How do we put 2 into a factor? X minus 2. How do I put the negative 1 into a factor? That's going to be x minus negative 1 or x plus 1, right? What do we do with the 3i? Yeah, it's plus or minus 3i because imaginary factors always, always, always come in pairs. So we're going to do this as x minus 3i because that would be our factor of positive 3i. And we're going to have x minus negative 3i, which is x plus 3i. So when we have those imaginary factors, we still fill them in exactly the same way. But since I want my polynomial to only have real coefficients, no imaginary coefficients, I need to multiply the pieces that have i's in them. So I'm not going to multiply these two factors. I'm leaving them as their little linear factors. That's what these are, linear. But this guy has i's, so these aren't going to work. So when we multiply these out, what are we going to get? Say it again. X squared. It's like minus 9i squared. But I squared actually equals, I squared is negative 1. So this is going to turn into x squared plus 9. Because remember, I squared is negative 1. So that's minus 9 times negative 1. So our polynomial that is irreducible is going to be our x plus 1, our x minus 2, and our x squared plus 9 as our function, as our p of x, f of x, whatever you want to call it. I guess they do say f of x in the instructions, so I'm going to switch to an f just because they say f. So we're multiplying out those complex roots. We've done this with i's before, but that is true for all of our complex roots. They don't just have to be imaginary numbers. We might have complex numbers. And that means we're going to use those conjugate pairs. So one's going to have a plus the factor, one's going to have a minus of the factor. Questions on this first one? We've done it with imaginaries before. I know what we're going to see next. Complex numbers. So, same instructions. This time we have zeros at 0 And 4 minus I. It's a complex number. So this is going to be one factor, and this is going to be another factor. 4 minus I is our complex root. So when we're putting this into the factored form, what we're going to have is plus or minus 4 minus I. Our complex roots always come in pairs. So when we're putting this into our factored form, we're going to have our x minus 0. That's our first one. There's our real factor. And we're going to have our x minus 4 minus I. And, I'm sorry, I actually made a mistake up here. It is not plus or minus of this. It is this piece and its conjugate. So think about when we would have to rationalize the denominator to make the i's disappear, because that's what we want to happen. So we need and its conjugate. So not plus or minus. I have it marked wrong in my notes. So I'm going to cross that out so I don't do that again. And its conjugate. So what is the conjugate of 4 minus I? Say it louder. 4 plus I. So the 4 minus I and its conjugate. So we're going to have our x minus 4 minus I. And we're going to have x minus this guy, the 4 plus I. So it's got to be the conjugate, not plus or minus of the factor, plus or minus of the conjugate. So we're subtracting both of those complex numbers. Because when we do that, and then we need to multiply out to get rid of those i's, all of our i's should wind up canceling out. So we do need to multiply this out to get our factors properly. So we're going to start by distributing our minus signs through on both of these, just because we have a lot of pieces here. So we're going to have x minus 4 plus I times x minus 4 minus I. Bless you. When we multiply this out, it's trinomial times a trinomial, so we're going to have a lot of pieces here. So x times x gives me x squared. X times minus 4 is minus 4x. X times minus I is minus ix. So that's my x times everything in the second pair. Then I'm going to take my minus 4 times everything. Minus 4 times x, we get minus 4x. Minus 4 times minus 4 is positive 16. Minus 4 times minus I is plus 4I. Then we're going to take our I times everybody, and we're almost there. So we're going to have plus I times x, so ix, minus 4 times I, so minus 4I. And I times minus I is minus I squared. What do we notice in this piece once we've got all these pieces multiplied out? I've got a minus 4I and a plus 4I, so those guys cancel out. I've got a minus ix and a positive ix. Those guys cancel out. And then we also know I squared. So this is minus I squared, so minus negative 1. This piece is going to become a plus 1. So when we simplify this and combine some like terms, what is this simplified as much as we can get? X squared minus 8x plus 17. And then we also have our factor up here of x minus 0, also known as x. So our function, our f of x, in its irreducible form. There's not another way I could write this without finding those complex roots, because that quadratic does not factor. The only way we could find those roots is to quadratic formula it to get those complex roots. So when we have complex numbers, it is super duper important not to do plus or minus on the factor. It's to take the complex number and its conjugate. Super duper important, okay? Because the instinct is to just do plus or minus, exactly like how I almost did it at the beginning and made a mistake. That's the instinct. Okay? It's not going to be something we have super duper commonly, but it can pop up every now and then. Questions on that bit? Because most of what we're doing today is not that bit. So we're going to have another, like it feels like a lot of definition. And this is going to be a tool we use a lot. If all we write is the very bottom row, I get that. But what this is this is a way of us taking a polynomial with some large number of roots, especially like 5, 6, 7 degree polynomials, and lets us find all of our possible options so that we're not just guessing blindly into the world of all real numbers. It's taking the list of all real numbers that exist and making a list of options for us. So this is for polynomials that have integer coefficients. So they only have real numbers. So that's why we never ever put complex numbers in our polynomials without multiplying them into the real parts. So we're going to deal with our integer coefficients. And what we're looking at here is we're going to be looking at the ratio, so the fraction, of factors of our constant, so the number at the very, very end, and factors of our leading coefficient. So what they're talking about is if I have some polynomial, p of x, it's going to have our leading coefficient is going to be q of x to the whatever. I'm just going to call it n. So it's our leading coefficient there, plus da 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 da, all of our gobbledygook in the middle. And then at the very end, it's going to say plus some number constant. We call it p. So all of our rational zeros, so our integers or our fractions, are going to be ratios of factors of our constant, p, the number at the end, the very last one, over the factors of the leading coefficient, q, the number at the very, very front. So we're going to wind up with lists of what feel like a lot of options, but when you compare that to all real numbers in the existence of the universe, it's significantly fewer options. So what we're going to do is I'm going to give you a polynomial, and we are going to make a list of all possible rational values it could have. So you want to make sure you have at the very least this part, because this is going to be a thing we use for a long time. For at least the next 3 days. 4 days. I could keep going. Okay, so we're going to start with this polynomial here. We've got f of x equals 2x cubed plus 11x squared minus 7x minus 6. And we are going to make a list, just list all, of the possible rational roots, possible rational zeros. So what we're going to do is we are going to find the factors of the constant. So our constant here is 6. And we're going to find factors of our leading coefficient. What's our leading coefficient? 2. So I'm going to start just making a list of that. Factors of P. So that is my constant. So in this case, it's factors of 6. What are factors of 6? 1. Yep. Positive and negative 1. Positive and negative 2. Positive and negative 3. Positive and negative 6. Those are all of our factors of 6. I could find pieces in there that multiply together to make 6. What's up? So then we're going to do the same thing with factors of Q. Our Q in this case is 2, our leading coefficient. What are our factors of 2? Yep, 1 and 2. So to find our list of all possible roots, we are going to make fractions of all of those options. So, all possible rational zeros and so we're just going to kind of play match them up and say it's factors of P over factors of Q. So I'm going to say it could be 1 over 1. So we could have plus or minus 1 over 1, which simplifies down to be 1. Or we could have 2 over 1. So plus or minus 2 over 1. Plus or minus 3 over 1, which is the same thing as 3. Oh, I made it small. We're going to have our plus or minus 6 over 1. So that's 6. And then we need to do the same thing, but over 2. So plus or minus 1 over 2. So plus or minus 1 half. Then our next one is 2 over 2. Well, that simplifies down to 1. We already have 1 written down, so we don't have to write it again. But then we have plus or minus 3 over 2. So 3 halves. And then plus or minus 6 over 2. Well, that would be 3. We already have 3 up there. So all of our possible rational zeros is this list right here. So these are all of the roots that we could find that were rational. Everything other than this would have to be quadratic formula, being super gross, decimally awfulness. Yes, dear?
The numbers of the possible zeros always going to have them.
Not always. The all possible, we're going to have a lot of them. When we start finding our number of roots, that's when we would have our degree. So the number of roots that actually work, we should have 3 roots because this is a cubic. But our all possibles, we are going to have sometimes where we have lists. Because there's a lot of options. We would just have to go through and try and figure out which of these, 1, 2, 3, 4, 5, 6, 12, because plus or minus, 12 options we have here that could be real roots of this polynomial. Which then we could start to use like maybe Descartes to kind of reduce our number of options and see things we have. So it's going to start kind of mixing things together. But we're going to practice this part again before we look at that part. Questions on this first one? Because we're going to do another one. Very, very much like it. Okay. So here's our next one. We're again going to make our list of all possible rational zeros. So we're going to do factors of our constant over factors of our leading coefficient. When you're doing your list of factors of P and Q, you don't have to include the plus or minus. You guys were doing that really good on the first one, so I was just kind of rocking and rolling with it. When we get into our all possibles, we do need to include the plus or minus for sure right there. But if you're just doing your factors of P and your factors of Q, I don't care if you do the plus or minus there or not. So we need our factors of P. Ooh, that's not a pen. What is the value of our P? 12. So our factors of 12 are what? 1, 4. Yep. 1, 2, 3, 4, 6, and 12. And if you do them in a different order, that's fine. If it helps you think about it as, okay, it was 1 times 12, and 2 times 6, and 3 times 4, and write them in that order, that's 100% okay. I'm just taking them in the order y'all give them to me. What about our factors of Q? What is the value of our Q first? It's 10. So what are our factors of 10? Yep, 1, 2, 5, and 10. And you can put the plus or minus here. That is totally fine. In our all possibles, you have to have the plus or minus. Here, it doesn't matter to me if you do or not. I would not take points off if you don't put plus or minus in our P and our Q. When we get into our all possibles, that's where it does matter. So our all possibles. And then we're going to take our ratios of P over Q. So I tend to just go down the line and take my P and I'll hit it with all the Q's. So I'll take 1 over 1, 1 over 2, 1 over 5, 1 over 10. And then I'll do the same thing with 2. 2 over 1, 2 over 2, 2 over 5, 2 over 10. I find that to be the easiest way to keep myself organized, but you do whatever works for you. But so this is going to be a really long list because we have 1 over 1, so we have plus or minus 1. Then we're going to have our plus or minus 1 over 2. So I'm on my blue, so we have 1 half. Then we're going to have plus or minus 1 over 5, so 1/5. And 1 over 10, so plus or minus 1/10. I'm just getting dots there. There we go. So that uses my 1 as my numerator. Then we're going to do the whole same process again using the 2. So 2 over 1 means we're going to have our plus or minus 2. 2 over 2, well, that's 1. I already have that in the list. We don't need to do anything there. 2 over 5, I don't have that one in there, so plus or minus 2/5. And 2 over 10, which is 1/5, we already have in the list, so I don't actually have to write anything new down. So some of them will repeat, and that's okay. So that used this 2 with all of these denominators. So now we're going to look at this 3 as our numerator. So we're going to have our 3 over 1. We're going to have our plus or minus 3. We've got 3 over 2, which I don't have in my list yet. So we're going to have plus or minus 3/2. 3 over 5, don't have anything for that yet. So plus or minus 3/5. And 3 over 10, I don't have that one either. So plus or minus 3/10. Because it won't simplify down. And we're halfway through our number of factors of 12. So like I said, these can be really long. I'm just going to go on to the next row, just so that we can kind of keep things organized. So I'm going to have my 4 as my numerator, 4 over 1. I don't have that yet, so plus or minus 4. 4 over 2. That's 2. I already have that in the list, so we're good there. Plus or minus 4 over 5. I don't have 4/5 yet at this point, so we need that. 4 over 10. What would that simplify down to be? 2/5. I already have 2/5. We're good to go. So those are the only pieces I need for my 4 numerator. Same vibe with the 6, plus or minus 6 over 1. That I don't have in here yet, so we need to make sure we get that. So plus or minus 6. 6 over 2. That's just 3. We've got 3. It's already in there. Then we're going to have 6 over 5. Don't have that yet. We're going to have plus or minus 6/5. And then 6 over 10, which simplifies down to be what? 3/5. I've already got 3/5. So that's everything with my 6 as a numerator. So then let's look at 12. 12 over 1, I definitely don't have that yet, so plus or minus 12. 12 over 2, well, that's just 6. I already have that one in there. 12 over 5. 12/5 is not the same thing as 6/5. Does 12 over 5 simplify? So I don't already have it in my list. Yes.
Oh, I thought you said
12 over 5 does not simplify.
Oh,
12 over 10. How about that one?
yeah, 6/5.
Yeah, that's 6/5. There we go. That one we already have on the list. I'd be like, oh no. So this is our list of all possible rational roots. So it is a big list. Sometimes these lists get real long. But even still, with a list this long, this is less than all real numbers. This is taking the list of all possible real numbers and saying, well, it's limited to this, so it's less gross. It's not perfect, but it's less. Okay, because what we're going to use this for is taking polynomials and trying to find our roots. And so that's what we're going to practice next. Is I'm going to give us a polynomial and say, find all of the real roots. So we're going to start with this one. So we have x cubed plus 2x squared minus 7x minus 4. And it says to find all of the real zeros of f of x. What's up? Huh? Yes. If I read it wrong, then I'm sorry. X cubed minus 2x squared minus 7x minus 4. So, let's find our possible values, our all possible real roots. So, what is our p? 4. And what is our q? Q is 1. So our factors of 4 are 1, 2, and 4. 1, 2, and 4. What are our factors of q? It's just 1. So are all possible options, how would we set each of these up? But what we need to include with each of them is plus or minus 1 over 1, plus or minus 2 over 1, and plus or minus 4 over 1. So we only have 6 possible options here. Positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. I could just start plugging and chugging. However, I'm going to combine that with what we used last week with our Descartes rule of signs. So how many positive real roots is this going to have? 1, because we started positive, it changes to negative, and then it never changes again. So we know it's going to have 1 positive real root. count down by 2's. So it will have one positive real root. If we did our negatives, so if we substitute in negative x, the sign, so negative x cubed, the sign would stay, so we'd have our minus x cubed. Our x squared, the sign would not change here, so we'd have our 2x squared. Minus x, that would change the sign here, so this would become plus 7x minus 4. Just clarifying here, this is my f of minus x. Just substituted that in. So how many negative real roots could this have? Yeah, so we were negative, it switches to positive, then it switches back to negative. So we could have 2 or 0. So when we're substituting in values, which ones should we use? Should we use the positive values or should we use the negative values? We want to use negatives? We might not have any. What are we guaranteed to have? A positive. You can, absolutely. If you want to do all the negatives, go for it. We only have 6 options here anyway, but what if it was that last one? And none of those negative works? Ugh. So if we have one we're guaranteed to have one in, I do recommend using that direction. You don't have to. Again, your choice. But if I had one real root and 2 complex roots and you chose to start with our negatives, you would be having to go through probably all 6 of those. Because we could have complex roots here. So what we're going to do then is we are going to try substituting in. So f of 1, f of 2, f of 4. You can either do it as a straight up substitution, or you can do it with our synthetic division to do to get to our remainder of 0. Because if it's a root, f of that value would equal 0. So looking at our positive values, if we have f of, which one do you want to start with? 1. I heard that one first. So substituting in positive 1. So we'd have 1 cubed minus 2 times 1 squared minus 7 times 1 minus 4. What do we get? Well, if we put in 1, we'd have 1 minus 2 times 1, which is 2, minus 7 times 1, which is 7, minus 4. Still haven't had the right answer quite yet. Negative 12. So is 1 a root? No. So then let's do our next positive root. Because if it's a root, that piece would equal 0. Because our root theorem, it's kind of what we ended, it's why we can take our factors or our roots and make factors. We can do the same thing the other way. So if it's a root, f of that value will equal 0. So let's do f of 2. What do we get here? 2 cubed minus 2 times 2 squared minus 7 times 2 minus 4. Mm-hmm. Yeah, y'all can use calculators. That makes this section so much easier than trying to do this without calculators. Last year they did not get calculators in this book. So, just saying, use them. What would we get? Well, 2 cubed and 2 times 2 squared, those are definitely going to be the same value. Because that's 2 cubed minus 2 cubed. So we have minus 4 times 2 minus 14. Negative 18. So 2 is not a root. So we have all of our possible options. So that means we have to have 4. So instead of me plugging it in to find it, let's just do our division. Because we're going to need our leftover bit anyway. So I'm going to divide out that root of 4. So f of 4 Must be. So I want to divide out that 4 because we are trying to find all possible roots. So I'm going to divide it out. I'm going to use synthetic division because we're dealing with linear factors. It makes it a lot easier. So what are my coefficients that go across my synthetic division? Mm-hmm. -7 and -4. So the 1's going to drop. 1 times 4 is 4, and we start adding. 4 plus -2 is 2. 2 times 4 is 8, plus -7 is 1. 1 times 4 is 4, and when we add that together, we get 0. So we can use this to also show that 4 is a factor. Because its remainder is 0, we know that's a factor. So what do we have left over as a polynomial? X squared plus 2x plus 1. Could we factor this guy? Mm-hmm. Yeah. This is a perfect square trinomial. This one factors. So we don't necessarily have to use any more division to get there. What is this one factoring into? X plus 1 times x plus 1. So our real zeros that we're asked for, our real roots, what are our zeros? 4 and -1. What's special about -1? It has a multiplicity of 2. So we could write this in factored form if we wanted to. It'd be our x plus 1, and our root of 4. So we'd have x minus 4. That would be our f of x in factored form. So we can take these polynomials, even if they're unfactorable, because I couldn't do this one with factoring by grouping. It doesn't work. And I can still get this in factored form using these possible options. Okay? And we are going to practice with this more tomorrow. I promise. Because these are weird and they take some practice. Okay? So here is the information for 4.4. Well, think about our lists of all possible reals. Those lists are long. They're not super difficult because we're just taking lists of fractions, but they can get long.
Are you going to take up the whole paper? How many sheets of paper am I going?
Let me see what I did for 4.4.
Wait, that binder has all of the answers.
It has everything. I used 3 pages for homework 4.4. But that includes all of my showing work and all of my arrows and trying to keep things in a logical progression. So we will practice more with this tomorrow.